All right, good morning, everyone. So, first midterm on Friday, right? Everyone knows that. There are a few questions on what constitutes your notes. If you can print it out or write it on a piece of paper, it's notes. So that means all previous homeworks, all previous homework solutions, your homework assignments, what's been posted as the official homework solutions on Carmen. That all counts in terms of notes. Homeworks, etc., from your previous classes. If you want to bring in notes from 3260, that's fine as well. Okay, so basically, if it's written down and it's on a piece of paper, it's good to go. Right. Any questions about that? Yes? How many people will be using a laptop? Or some sort of, yeah, or a tablet, yeah, both. Hands up high. It's not that many. Okay. I was worried about getting 30 emails today. So basically, if you're going to bring a tablet or a laptop, sit in the front of class. That's, Thursday night I'll be sending the basic cover sheet of the exam, and also it's going to be the back as well, which is information. You'll see the rules for the test. I'll tell you that if you're going to use electronic devices, you're going to have to get in front. Any other questions about the exam? Okay. So also, there's been a lot of questions about the content. Again, this spans basically from the beginning of class to homework 4. I don't know if I made this explicitly clear, but project 1 is overlapping with homeworks 1 through 4. Right? There's nothing on there that wasn't on homeworks 1 through 4. Right? So project 1 would be fair game as well. Okay, we did have linearization, but we also have linearization on homework 1. Okay. Yes?
So if there was a linear question, how many people would you have to do it? So that like in that it was like.
Oh no, I guess I don't consider that again. Okay. So on Monday's class, we were neck deep in this problem on it's a, for one, just kind of go back to where we were. It was a shunt motor, right? And we are ultimately trying to get the transfer function for shunt motor connected to a rotational inertia. Right, so if we go back up to what this system looks like from more of a schematic point of view, it's on the bottom left here. We have a shunt motor given by the bottom left, which is, we're giving the electrical diagram for a shunt motor. Then we have a rotary inertia, rotational inertia. And we're trying to look at the coupling between these two different systems to describe then the transfer function between voltage in, that's our input, right? So that's going to be the denominator of our transfer function, to the output, which is the position theta of our motor, which is our output. Right? Okay, so where we were at on Monday when we adjourned is we had just done a very careful job of going through the linearization for function 1. And just so you can see all the functions up here in the upper left is function 1. We did a careful job describing then the differential equation for, or the linearization for this equation. We then very quickly did function 2. Function 2 is completely linear, so the linearization of a linear function is really simple. It's just itself. And then we very quickly, before class ended, we did 3, and so I wanted to just make sure this is all clear. So this is the correct answer here, but I wanted to erase this so we can then go through this carefully so everyone's on the same page here. Okay, so a lot of you probably already have this in your notes because we went through this already, but this is the more careful way to go about it. So we'd say that function 3 if we look at the terms of function 3, we have IA, we have D, IA, dt as a term. We have IF, we have theta dot, and then we also have v in function 3. These are all the terms that vary in time in function 3. Right? And if we were then now do linearization, we would follow the template, basic template we have up at the top here. We would first evaluate this function at all the operating points. So just following this down, this would be RA IA bar plus LA D IA bar dt plus KA KS IF theta bar dot. Right. We'll get to the right-hand side in a little bit, but here's what we have on the left-hand side of function 3, right? Evaluate the operating points. So we know a few things. One, that we know the change in current going through the armature with respect to time is equal to 0. Oh, sorry, the change of the steady operating point of the current going through the armature is equal to 0, right? Because we're saying this is evaluated at an operating point or a steady state, right? So next, we are looking at then going through every single term and then doing linearization. Yes? Thanks. Yeah, I missed that. Show bar. Thank you. All right. So, yes.
So if you have IA dot by itself and then you bar it, is the dot go above the bar or below the bar?
In my mind, it doesn't really matter too much.
Okay, so it's the same.
Yeah. So I mean, I guess technically it would be IA dot bar, but in my mind they're interchangeable. Yeah. So it's just two denotations, Ron. One the bar denotes operating point. The other one denotes that we're talking about the time derivative, right? Okay. So very first thing we're going to do is we're looking at this, and then we're looking at the partial with respect to the very first term. So the very first term, the way I defined it, you of course could say the set of arguments are, say, dia dt ia, right? You could switch the order, it doesn't really matter because we're summing everything together anyhow. But the way we wrote it here is function 3 is first a function of ia, so we're going to take the partial of this expression with respect to ia. We only see this pop up once, right? So this is going to give us plus RA, and then the deviation, IA minus IA bar. And that's it. There are no other terms as a function of IA, right? Next term of this list is DIA dt. Okay, partial of this expression with respect to that term. There's only one term as well. Okay, so then we have LA times then the deviation from the operating point. Next term in here is IF. So here's where it gets a little bit more complicated, right? So if I take the partial of this expression with respect to IF, I get then KA, KS, theta dot, right? I evaluate this function now at its operating point, so I get then KA, KS, theta bar dot, then times IF minus IF bar. Next term, theta dot. Partial of this expression to theta dot with respect to theta dot is KA, KS, IF. And then the deviation. Okay. Last thing, we have to look at the right-hand side of this equation. I ran myself out of room, but I'll try and squeeze in at the bottom. Right-hand side, we have then function evaluated at the operating point, that's v bar, then plus this function with the derivative with respect, or the partial with respect to v. So partial with respect to v of v is just 1, and then the deviation. All right. So this is the long form, right, of doing the linearization. I mean, not long form, this is the form, but this is going through every single little step. I think once you get good at this, you'll see how you can economize a little bit, and you'll see some patterns emerge. Certain things always cancel out. It's going to make your life easier, but this is going through it very carefully. Okay, so in terms of things that are going to go away for us, first off, we have this expression, which is the whole function 3 evaluated at steady state. So we have the RA IA bar plus KA KS IF bar omega bar is equal to V bar. All right. And so we see all of these terms here. So this term plus this term cancels with this term here. Then given our coordinate transformations that we defined, we have that this entire quantity here goes to IA hat. This quantity here, well, sorry, I forgot to mention, this goes away too. All right, this quantity goes to DIA hat dt. This one goes to IF hat. This one goes to omega dot hat or hat dot, and then the last one, V hat. Okay, so I had to add an extra page that I ran myself out of room, but then equation 3, actually it may make sense to put all these equations together. Okay, so just putting all equations 1 through 3, the linearized forms together so you can see them all at once. Okay, so this is our first equation linearized, second equation linearized, and then third one. Okay, these are our 3 equations. Okay, so as you can see that writing these hats kind of get annoying sometimes, so if you ever want to drop the hats, once you have everything in hat variables, you would just write somewhere on your paper, say drop hats for convenience. Okay, and so what you should have seen in your project part 1 is that you can't forget that you did this transformation, right? So say for instance your operating point for your current is some really heavy duty machinery piece, and then the current going through your system is 200 amps, which is enough to kill you many times over. That's a ton of current, right? And you're doing some sort of analysis and you get that, and you solve for your current, and you're solving in terms of hat variables, and you get a current value of 5, right? You can't forget that actually your current value is 200 plus 5. 5 and 205 are very different numbers, right? So you can't forget that you did this transformation, right? It's actually very important in terms of actually ever applying this to some sort of physical system, right? All right, but if it makes your life easier, you want to drop these hats, just make sure it's very clearly denoted on your paper that you've done so. Right? Okay. All right, any questions about the linearization portion of this? Okay. So ultimately here we're trying to get to a transfer function, so that means we need to take the Laplace transform of these functions. And so next step then is, if we're looking at transfer function, remember transfer function defined as ratio of output over input of the Laplace transform taken for initial conditions all equal to 0, right? So assuming all initial conditions are equal to 0, take Laplace transform. Laplace transform. So this is going to give us then, just going line by line here. Where's my cursor? Js squared theta of s plus cs theta of s minus k tau ks. Now keep in mind this IA bar is a constant, right? So you treat this exactly the same as you would the k tau, the ks, etc. This IF, however, is not a constant, right? This is a function in time, right? So when we take the Laplace transform of that, it becomes IF of s, and then minus k tau, ks, IF bar, IA of s, all equal to 0. Sorry, forgot to mention logistics-wise today. I mentioned this like maybe a week ago or so. Today's recitation is review, right? This is on the syllabus as well. Review for the midterm. Show up when you want, leave when you want. There's no attendance. It's just for your benefit. If you have questions you'd like to ask, bring them. No real structure. So what I mean, show up when you want, leave when you want. If you're in the 4 o'clock section, you can show up at 3 o'clock, 4 o'clock, whatever works for you. I'll be there from 3 to 6:20 or whatever it goes to. Okay. All right. Second item for these Laplace transforms. This next one's gonna be RF IFS. Plus LF SIF of S equals V of S. And then last one. Okay, so now we have, if we're kind of catalog what we have here, we have three equations, right? So we have three Laplace transforms, which is three equations. We have three unknowns. And so the unknowns are IA, IF, and omega, right? And also we have a bunch of constants, and then we have one known. And so we'll talk about this for a second, why I'm saying that we know V. Okay. So what we're looking for is ultimately we're looking at this ratio of theta over V. V would often be specified, right? So if we have some sort of transfer function and we ever want to solve for theta, we would have to have V to ever solve for theta, right? So we're going to treat V in this case as a known, right, when we're trying to solve this. And the structure that we're going to use is we're going to put this in matrix form. You don't have to do it this way, but we're going to put it in matrix form so we can use Cramer's rule. And it's going to make it a lot easier to solve, especially when we get up to the 3x3 case. 2x2 cases you can solve just by solving for one variable, substituting the other pretty easily. But by the time you get to 3x3, it gets fairly complicated, and Cramer's rule is probably going to be your most efficient way to solve this. And so this is going to be a matrix of coefficients. This is going to be unknowns. This is going to be your vector of unknowns, and then you're going to have then your vector of knowns on the right-hand side. Okay, that's going to be the basic structure we're going to look at doing it. Okay, so trying to get everything on one page here so you can compare back and forth. Okay, so first equation, we look at filling out this matrix, right? I'm going to create this big matrix. Okay, so my unknowns, we said, were IA. Well, sorry, we'll do it in the order of my notes. Doesn't really matter what the order you choose. It's going to be theta, IF, IA. Okay, so if we look at this first equation, terms that are coefficients on theta are js squared plus c. So that's going to go in the 1, 1 entry of this matrix. Js squared plus cs. Terms with the coefficient, terms that are coefficient on IF are negative k tau ks IA bar. And then lastly, coefficients on IA, negative k tau ks IF bar. Right-hand side of this equation, or what's known, there's nothing in this particular equation, so the right-hand side is going to be equal to 0. Second equation, we only have terms in terms of IF, right? Nothing else. It's going to be LF S plus RF Right-hand side of this is V of S. All right, last equation, we have a single term, which has a coefficients on theta. So Ka, Ks, IF bar. And now we have a term on IF. And then lastly, terms on IA. And this all equals V. Okay, so this is just, we've done nothing. It's in terms of operations. All we've done is taken 3 independent equations and put them in linear algebra form, matrix vector form. Karsten. Bottom left term. Yes, thank you. Missing that. All right, so ultimately what we're trying to get to is theta over V. So we're trying to use Cramer's rule to then solve for the very first term of this, right? So we could solve for IF, we could solve for IA. Oftentimes we may not care, right? Especially the problem statement says try and find the transfer function for theta over V, right? So you may care as an engineer in terms of making sure you're not going to put a current, IA or IF, that's so strong you're going to blow up your system, but for the purposes of this class, oftentimes the problems won't be asking for those intermediate values, right? Or solutions to intermediate values. Right. So this problem statement says solve for theta over V. So that means we're only solving for the first term here. IF and IA will be something, but we're not going to care what they are. So that's what's really great about Cramer's rules. It allows you to solve for a single variable without really caring what the other variables are. Right. So we'll never solve, at least the way we're going to do it right now, we're not going to solve for IF or IA. So if we want to know what is theta of S, all right, so theta is the first term in our unknowns. That means we're going to substitute the formula for this for using Cramer's rule. Is we're going to let me move this down a little bit. I didn't give myself enough room. Okay, so we're going to make up a new matrix in which we replace the first column, because we're solving for the first term in this vector, with the solution vector. So the first column is going to be 0, V, V. Second and third columns are going to follow identically. Okay, denominator is just going to be the determinant of this coefficient matrix itself. If we say this is equal to AX is equal to B, it's just the determinant of A. Okay, so determinant of a 3 by 3 matrix. Maybe you saw this in statics. That's the last time I think. That's trying to think of back when I was undergrad when we first saw determinants of 3 by 3 matrices, maybe in linear algebra, your linear algebra class. It's basically a pattern that you follow, right? So if I want to know what's the determinant of this generic 3 by 3 matrix here, it's going to be, let's use different colors here to mark this. All right, so it's going to be then A times the determinant of this lower right 3 by 3 matrix. That means I'm going to have then A EI minus HF, right, times in the center term, we'll use, say, triangles to denote this one. Actually, use a different color. Times the determinant of the 2 by 2 matrix composed of these entries. And then the biggest difference here is that it's actually negative then, B DI minus GF. Then C times the determinant of then this 2 by 2 matrix in the lower left. Okay, so then if you go 4 by 4, there's a pattern to that one, 5 by 5, etc. It keeps on going up. We won't see anything higher than 3 by 3 in this class. Okay, so then if we want to know what is the determinant of then, or if we want to solve for theta of S. Okay, so the very first term, right, if I'm doing the determinant of the numerator, it's going to be 0 times this lower right determinant, right? That's going to be 0. Nothing happened there. Then it's going to be then plus K tau Ks IA bar, and then the determinant of the 2 by 2 matrix composed of VV and 0 LAS plus RA, right? And so then that's just going to be result in then LAS plus RA V. All right. Then we have this next term, which is going to be negative K tau Ks IF bar. Whew, man. Multiplied by the quantity then LF S plus RF minus KA KS mega bar, all multiplied by V, right, in the numerator. Sorry, I was double checking really quick. I may have a negative sign flipped here. No, that looks correct. No, I do have a negative sign flipped. Okay, so that's the numerator. Denominator is going to be a little longer. Okay, so JS squared plus CS times the determinant of this lower right matrix. So that brings a negative, sorry, it's a positive. So that's going to be then, lower right matrix is going to be then LFS plus RF, LAS plus RA. Then we have 0 here, which kills the cross term, right? Then we have positive K tau KSIA, determinant of this term and this term, but those both have zeros in the upper entry, so that's going to result in nothing happening actually. And then lastly, minus K tau KS IF bar, determinant composed of this lower left matrix. This is 0 times this, that goes away, so then this is going to be the negative, turns the front into a positive, LFS plus RF, KA, KS, IF bar, S. Right. So it takes a while, right? We have a lot of terms in here. All right, so I guess my only advice here is that we have a lot of coefficients. We're going to use software tools to try and then make this a little bit more tractable. And we're going to start, as we build up throughout the class, we're going to be looking at pole locations, zero location, what that means in terms of behavior, right? So we have a lot of, it's really tough to just make sense of this, looking at this and trying to understand what's going on, but we're going to work on that in terms of looking at pole locations, et cetera, and make sense of what's going on here. So trying to make sense of what's going on here, first off, note that we have a V in the numerator on both this first term here and second term here, right? So we can divide out by V. To save on me writing all this and causing a lot of boredom in the classroom by watching me just write notes, so I'm just going to divide this out. This is theta over V. So it gets rid of that term. That gets rid of that term right there. Right? And so in terms of the problem statement asks for, it says find the transfer function between theta and V. And this is the answer. Okay. Right. So a lot of work, but this is, we're starting to connect a lot of systems together. It gets fairly complex. Right? Any questions about what we did here? We'll talk a little bit about what this equation means in a second. But any questions about kind of the mechanics or the way in which you move through a problem like this? Yes?
For the Kramer's rule, like when it has like A, B, and C, it's supposed to be like minus B and then minus C, like times the second determinant. Like after it has like A times the determinant, minus B times the determinant, and is it minus C times the determinant or plus? Like it's hidden. Like I was wondering if it's plus or
It's plus. Sorry, oh, jeez. The cyan comes out much better on my screen. I didn't realize that's not part of the read. Okay. Yes.
Right, so then if it's plus, shouldn't go to the last string as being negative? Because they're both like multiplied by negative K tau KS I.
Yeah, so then the reason why it's not is because if we look at this term, right, it's this, right, negative K tau KSIF, multiplied by the determinant here, right? So then it's plus
Oh, so it's
this
negative.
minus this. Yes.
So for Kramer's rule, we have to set it up, if we want to use it like the way you used it, do we have to make our first variable be the one we want to solve for?
No, it could be any variable, right? So for this, yeah, so it's you replace. If you go back to, I forget what note set it was, it gives a more generic formula for Kramer's rule. But say, for instance, instead we wanted to solve for IF, right? Because you wanted to know the current in the field, right? Dynamically. You would, instead of put the solution vector in the first column, you would put it in the second column. Because IF is the second in this vector. And then also going to IA, 0BV would go in this column here. Right? So you don't have to set it up the way we did. Right? We could have rearranged the order of the unknowns. Any other questions about kind of the mechanics of doing this? Okay. So they're not independent variables, right? So if we talk about the only independent variable we have here is V, right? That's our voltage that we're setting in the system. So we're looking at basically theta and theta, IF, IA are solutions to this differential equation once we know V, right? Right. So V we can independently tune. This is, say you have some sort of function voltage generator sitting on your desk and you have this motor set up, right? If you put some sort of voltage spike into your system, the current going through the armature of the field and also the position, if it's following these equations correctly, it should have some sort of trajectory or path associated with it. And those are the solutions given the V you specified. So V is your independent variable. Theta, IF, IA are all solutions or therefore dependent variables. Okay, so just some notes on this expression here. If we look at the numerator and denominator here, we can start to talk a little bit about some sort of behaviors that we would expect to have for the system. So notes on behavior of the system. Okay, so first one is that if we look at the denominator, so first off, okay, so we have the numerator, and we have some terms that are constant. So say for instance we have, some terms are s to the 0 terms, or are not multiplied by an s. Like for instance, k tau ks IA bar times RA, right? That's going to result in a s to the 0 term. So the numerator is type 0. The denominator, or the entire system, is type 1. Okay, so if we look at this equation here, we have s squared cs, and then we could pull out s to the 0 terms here, but it's always going to be multiplied by s in the denominator. Same thing with the second term in the denominator. We have an s here, right? So we're always going to have a pole at the origin, oftentimes called a free integrator. So keep in mind, if you want to integrate a function, you divide by s, hence the name free integrator. And so this is a type 0 system. Or sorry, type 1 system. Okay, so type 1 systems, for the fairly basic systems we're talking about in this class, in terms of fairly simple configurations of just a few pieces, this is very characteristic of systems without springs in them. Then we'll say systems without springs or capacitors attached to ground. Okay, so if we have a type 1 system, we're going to have a solution that somewhere in the solution is going to have, it can have a lot of things, right? It can have a lot of oscillatory terms, exponential decay terms, etc. But somewhere in the solution, because we have a pole at the origin, when we solve for theta of t, it's going to be a lot of things plus some unknown times u of t, right? Coming from the inverse Laplace transform of 1 over s. Okay. All right, so what this says, if we go back to the original description of our system, all right, so say for instance, I were to have this motor, it's on my desk, I have some sort of rotational inertia, this has damping in it, and I were to put a voltage across the terminal of my motor for say 10 seconds, and then turn the voltage off, right? That's kind of a little experiment I'm going to do. The motor is going to spin, 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 right? It's going to get to some sort of velocity. I turn off the motor, and all of a sudden it's going to keep on spinning, but it's going to slowly decrease in velocity to where it just stops, right? So the velocity went to 0 over time. The position is now some fairly large number because it kept on spinning, and so that's, every revolution it goes to 2 pi radians, right? And so now the long-term solution is going to be something that's not 0. If I had a spring in the system, right, I put this voltage in, the spring is always going to drive the position back down to 0. Okay? So systems that don't have springs or capacitors in them, very characteristically are going to have be type 1 or have a free integrator. Okay, and that is directly results in the solution that this C u of t, this is a constant, and this is going to persist for all time, right? So if I go to times equal to infinity, my solution, assuming that everything else decays, the solution is going to be C. Right? Other notes, 4 poles and 1 0. Okay, so four poles and 1 0, so I have 1 0, this must be real. So the 0 must be real, so if I look at the pole 0 map for the system, we haven't assigned numbers to this. I'm just really making up location as we go, but just kind of give you an idea of the landscape. We have a real 0. We'll just assume it's in the left half plane for now. We have then also, we know that we have one of these poles, one at origin, just from the discussion we just had. And so then the 3 remaining so we can have 2 different options there. We can have so we can have 3 real, or we can have 1 real, 2 complex. All right, those are our options. So assuming that, we can just kind of given some general behaviors here. Say, for instance, we have a real pole on the left-hand side and then 2 complex. We're talking about this type of landscape for our solution, right? In terms of pole 0 locations. I'm putting everything in the left half plane, especially for the poles, because just kind of understanding how the system behaves. So we only have losses in the system. We don't have anything that actually has some sort of amplification factor here. So we only have resistors and dampers. We don't have anything that gains energy in the system. And so when we have that characteristic, all the poles are going to be in the left half plane or at the origin, right? We don't have something that has an amplifier or some aspect that causes right half plane poles in the system. Okay. So only losses. So if you can imagine, I have the system on my desk. If I were to put voltage into the system for a little bit, it's going to spin up. I turn the voltage off. The velocity is going to decay to 0, right? It would be very unreasonable if I pull that voltage off and it keeps on going faster and faster and faster, right? You would not expect that to happen. Okay. The rest of the notes goes into the Bodhi plot for this. We've seen a lot of Bodhi plots thus far. I don't know if that's too important to look at that. So I wanted to just take the last 4 minutes before we get into AC type motors, which is kind of a new subject, just open it up to any questions you have about what we just did now in terms of getting the transfer function for this fairly complex system, or any questions you may have, general questions about the exam. We don't have time to really answer a specific question like, do problem 8 of the review sheet, because we have 4 minutes left, so we have to reserve that to the review session later on today. So any questions about this or the exam? Yes?
So with the full axis curve dominating the response, and how that works?
So there's not really like a terminology in terms of what dominates the frequency response. That's not really a metric that we really talk about. What it would do is we know that, I go to the blank Bodhi plot we have for this. The entire notes are online, already filled out, but we do know something about a pole at the origin, right? So pole at the origin has a phase of negative 90 degrees. And then it has a slope of negative 20 dB per decade, right? Okay, so, I mean, if we say dominate means that like it really fundamentally changes the shape of the Bodhi plot, yes, it does. But, I mean, we'd have to look at the actual other terms and say, all right, what others make meaningful changes to the Bodhi plot? Like we could have, dominate's kind of a funny word. That's not really something how we describe a certain term in it, but it will have this characteristic. If you kind of want to tie this experiment of this system on my desk, right? If I were to just put a voltage across the terminals, right? That's a step function. We think of that, say, as also equivalent to saying whatever the value of that voltage is times cosine 0t, right? So that is very, very low frequency signal for an indoor system, right? So if I look at very, very low frequency signals, that's off the chart to the left here, right? So if I look at what is the magnitude of the response for a low frequency signal, it's infinity, right? So if I were to just put a voltage across the system and hold it for all time, the motor is just going to keep on spinning and spinning and spinning, and the angle is going to eventually go to infinity, right? If I go for infinite amount of time, the angle is going to go to infinite, right? So that is, I guess, one characteristic. You want to try and tie like something that's fairly dominating of this Bodhi plot to something physical. Does that make sense?
Yeah.
Okay. Back here.
So I thought that Bodhi plots, like we were supposed to give a harmonic input.
Yeah.
Like that's what they're for. That's why we have like a frequency.
Yeah.
But we have like a DC motor, right? And we assumed also that we had like steady state stuff when we made our assumptions. So I'm kind of confused how those two line up. Like
Okay. So DC motors, I would argue, is maybe a slight misnomer. So it's DC in the sense that it can be run in DC mode, but we can also put a harmonic voltage into it. Right? So if you look at, and not harmonic, any voltage we want. So if you look at servo motors, a lot of them are DC motors, and that we have continually changing voltage all the time. Right? Kind of one of the hallmarks of a servo motors is continually adjusting the input to then change the position usually or velocity. So it's DC in that one of the AC motors may be a little bit more clear. AC motors, we're going to have a defined AC signal that's coming basically from your wall 60 hertz, right? DC can be anything.
Right. So does the transfer function tell us anything about like if we give it a steady voltage like of a certain value, does it tell you what kind of data you get out?
Yeah. So here, yeah. So a steady voltage is just a harmonic of extremely low frequency or zero frequency.
Okay.
Yeah.
All right.
That makes sense. So if you have just a DC voltage, you look at the long time, it's going to be infinity regardless, as long as your voltage is above 0. Okay, but if the Bode plot gives you the scaling between input and output, right? So you would, if you wanted to know the difference between the output between 1 volt and 2 volts, that's a doubling then of the output, right?
Oh, because we linearized it.
Yeah.
Okay.
Yeah. All right. With that, we're out of time. See you this afternoon if you want to show up. If not, see you bright and early Friday morning for the exam.